Right, so the other thing that I didn't do in the previous time I taught this class, and have to do therefore now, is volumes. So here's the idea. Definition. Let S be a solid region. I'm going to have to hold this and just look at my iPad. Solid region bounded by the lines x equals A and x equals B. For each x, such that x is greater than or equal to A and less than or equal to B, let A of x be the cross-sectional area of S. Okay, so to give you an idea of what I'm talking about so far, I'm saying we have these 2 points on the x-axis. They're called A and B. And we've got a solid region. So it looks something like this, maybe, or not. Doesn't really matter what it looks like. Point is that it's a solid region, so this has like, volume to it. Yeah, that doesn't look very good. Maybe if you draw it more like... Okay, that looks marginally better. You know, it's a big... It's a thing that has volume, right? Three-dimensional object. So, the volume of S is the integral V equals integral from A to B, A of x dx. All right, so the area of these curves, they're perpendicular to the x-axis. The area is given by A of x, so it's going to depend on what the x value is. I'm saying the volume is just going to be the integral of all those cross-sectional areas. Okay? And this can be understood as the definition of volume, because in truth, in high school, you never actually defined what volume was. You just kind of had this vague notion that it was like the amount of space contained in a figure, right? Well, there is a little more rigor that we can apply to that, and that's by defining this as an integral. All right? So what we're going to do today is we're going to take curves defined by functions in the xy plane and rotate them around lines to get solid regions. Then we'll find the volumes of these solid regions. These are called solids of revolution. Okay. So let's do an example or two, or more than two. So, example. So I've got the region bounded by y equals 1 over x, y equals 0, x equals 1, and x equals 4. Okay, so find the volume by revolving this region about the x-axis. So we're going to have to draw a diagram in order to have any idea what we're talking about. As always, there's a more detailed picture in my notes, but I'll just draw a crude sketch here. So y equals 1 over x is a curve that kind of looks like that. We're going to go from x equals 1 to x equals 4. So maybe like this sort of region. Okay, now you look at the region bounded by these things. And in the previous lecture, we'd just want to find that area. And that's, a valid problem too. But in this lecture, we want to do something different. What we want to do is take this region and rotate it around the x-axis. When you do that, so this whole region gets rotated around the x-axis. And when you do that, it's going to pass through some region of three-dimensional space, right? So this whole thing is being rotated around this x-axis, so it's going to encompass some region in three-dimensional space. We're trying to find the volume of that region. Okay? So that's what it means when we say revolve this around the x-axis and find the volume of that solid of revolution. Okay, so let's take off this motion blur because I think it'll confuse the diagram a little bit. So, the idea here is what you need to do is take a typical slice of this region that is perpendicular to the axis of rotation. This is called the disk and washer method of finding a volume of revolution. There's also the shell method, but we won't be talking about that today. So take a slice that's perpendicular to the axis of rotation. In this case, the axis of rotation is the x-axis, so we're going to take a slice perpendicular to that, so it should be vertical. When you rotate this around the x-axis, what you'll get is a disk. Okay? This rotates around the x-axis and you get some kind of disk shape. That is, the area of that disk is the cross-sectional area at this particular value of x. So first of all, let's figure out what that is. Area is pi r squared of a disk. In this case, r is the distance between the x-axis and this curve, but that would just be what we call the y-coordinate of the curve, so 1 over x. So pi 1 over x squared. Or in other words, pi over x squared. So this is the cross-sectional area of the solid. So just by definition of the volume is going to end up being the integral from 1 to 4 of this cross-sectional region. Cross-sectional area, sorry. So integral from 1 to 4 of pi over x squared. This is pi integral from 1 to 4, x to the negative 2, add 1 to the exponent and then divide by the new exponent. So we'll get negative pi x to the negative 1, evaluated from 1 to 4. So this is just negative pi times 1 over 4 minus 1 over 1. In other words, 3/4 pi. Okay? And that gives us the volume that you would get when you take this curve, evaluate from 1 to 4, and you spin it over the x-axis, like a piece of pottery. Okay? Let's do some more examples. This, by the way, is always how these problems work. You're just going to take a typical slice of the region that's perpendicular to the axis of rotation. That's going to give you some kind of either disk or washer. You're going to take the area of that disk or washer, and then just integrate that along the x-axis, okay? Or y-axis, depending on what the axis of rotation is. We'll get to that. Okay, so find the volume generated by rotating the region bounded by the curves y equals e to the x, y equals 0, x equals negative 1, and x equals 1 about the x-axis. Alright, so as usual, we should draw the situation so that we know what we're looking at. And as usual, this is just a crude sketch, while a more detailed diagram can be found in my notes. Y equals e to the x is a curve that kind of looks like that. X equals negative 1 is a vertical line. X equals 1 is also a vertical line. So we have a region that kind of looks like, well, it's the interior right here. So it kind of looks like this. That's the region. We're wanting to revolve that around the x-axis. So, once again, we're going to take a typical slice of this region that is perpendicular to the axis of rotation. In this case, the axis of rotation is the x-axis, so we want to take a vertical slice of this region. Okay? When you rotate that around the x-axis, what you'll get is some kind of disk. The area of that disk. Well, as usual, it's pi times the radius squared. In this case, the radius is going to be the distance between the x-axis and the curve, which is just e to the x. So this is pi e to the x squared. In other words, pi e to the 2x. The volume we're looking to get from -1 to 1, so the volume is just going to be the integral from -1 to 1 of pi e to the 2x. This is just pi over 2 e to the 2x, evaluated from -1 to 1. In our case, that just becomes pi over 2 times e to the 2 minus e to the -2. And that is our volume. Okay. Let's do another. So here we've got y equals the square root of 2x, x equals 0, and y equals 4. Okay. Y equals the square root of 2x is a curve that kind of looks like this. Y equals 4 is a horizontal line that kind of looks like this. And then x equals 0 is just the y-axis. So we are looking at this region right here. All right. So if we're going to revolve this around the x-axis, then we need to take a typical vertical slice of this region. But you might notice that this one is a little bit different. We take our vertical slice, it looks kind of like that. But then if you rotate that around the x-axis, that's not going to give you a disk. That's going to give you a washer, a disk with a hole in the center. So, rotate this around. This goes over a circular path. This goes over another circular path. And you get a washer. So, what is the area of a washer? Well, it's actually not that hard to find. All you have to do is just take the area of the outer circle minus the area of the inner circle. So, pi times the outer radius squared minus pi times the inner radius squared. Now, the outer radius, well, that would be the radius that's further away from the axis of rotation, so further away from the x-axis. That would be y equals 4. So pi times 4 squared, then minus pi times, okay, the inner radius is going to be on this curve, so that's going to be the square root of 2x. Okay. So this is just pi times 16 minus 2x. Or in other words, 2 pi times 8 minus x. So the volume is going to be the integral of 2 pi 8 minus x. As for the bounds, well, we're going to have to think about that for a second. So we're integrating along the x-axis. So the lower bound is 0, which is this point right here. The upper bound is the x-coordinate of that point right there. So this is from 0 up to whatever this x-coordinate is. This x-coordinate can be found by just setting these two curves equal to each other. So 4 equals the square root of 2x. In that case, 16 equals 2x. And so then x equals 8. So integral from 0 to 8. So we can take out the constant. This is 2 pi times the integral from 0 to 8 of 8 minus x. You do that antiderivative, you just get 2 pi times 8x minus 1/2 x squared, evaluated from 0 to 8. So this is just 2 pi times 8 is 64, minus 1/2 of 8 squared is also 64, minus 2 pi times 8 times 0, minus 1/2 of 0 squared. (64 minus 1/2 of 64 is 1/2 of 64. Multiply that by 2 and you get 64. So this becomes 64 pi. Okay. Let's do one that's slightly different now. So here it's the region bounded by y equals x cubed, y equals 1, x equals 2. But we're going to rotate it about the line y equals -3. So as always, we better draw a diagram to know what we're talking about here. And as always, the diagram in my notes will be better than this one. Y equals x cubed looks kind of like this. X equals 2 looks like this. Y equals 1 looks like something like this. And so what we're dealing with is this region right here. But we're not rotating it around the x-axis. We're rotating it around the line y equals -3, which is way down here. Okay. The procedure is the same, But now we have to be a little more conscious about what the inner and outer radii are. We take a typical slice of this region. When you rotate that around the line y equals -3, you're going to get some kind of circular washer. It's going to be pretty huge. Anyway, it loops back around, whatever. So, the inner radius is going to be the distance between this point and -3. Well, this is y equals 1, so 1 minus -3 is, this length is 4. So the inner radius is 4. As for the outer radius, well, the outer radius is going to be the distance between a point on this curve and -3. So normally we just say that's x cubed if we were revolving around the x-axis, but we're not. We're revolving around the point x equals or y equals -3. So what we've got to do here is add 3 more units to that. So x cubed plus 3. Okay. And so this can be written as pi times x to the 6th plus 6x cubed plus 9 minus 16. So then we have pi times x to the 6th plus 6x cubed minus 7. Okay, so our volume is going to be the integral of pi x to the 6th plus 6x cubed minus 7. And what are going to be the bounds? Well, based on the diagram, you can tell that the bounds are going to be the x-coordinate of this point right here up to this line, which is x equals 2. So upper bound is 2. Then we need the point of intersection between x cubed and y equals 1. So you set x cubed to be 1. And then, of course, x is 1. So the lower bound is 1. You do this antiderivative. This is pi times 1/7 x to the 7th plus 6/4 is 3/2. So 3/2 x to the 4th minus 7x, and this is evaluated from 1 up to 2. Okay. Well, literally, that means pi times 1/7 of 2 to the 7th plus 3/2 2 to the 4th minus 7 times 2 minus pi times 1/7 of 1 to the 7th plus 3/2 1 to the 4th minus 7 times 1. I don't really feel like doing the arithmetic there, but the answer is 471 pi over 14. The specific way that we happen to write that number, as I've been saying, is unimportant. Okay. Now let's do another one that's a little bit different. This one is the region bounded by x equals 2 minus y squared and x equals y to the fourth. And we're going to revolve that region about the y-axis now. All right, so that's a little bit different, right? First of all, we'll draw a diagram. X equals y to the fourth looks kind of like this. X equals 2 minus y squared looks kind of like this. We are asked to revolve this region around the y-axis and find the area. Okay? Just to be clear, the region we're talking about is like this. So what we've got to do is take, again, a typical slice of this region perpendicular to the axis of rotation. In this case, the axis of rotation is the y-axis, so we need a horizontal slice. Okay? When you revolve that around the y-axis, what you'll get is a washer. And so we need to find the area of that washer. The outer radius is going to be the distance between the y-axis and the curve x equals y to the fourth, which would, curve x equals 2 minus y squared, which is just going to be 2 minus y squared. Minus pi times inner radius is going to be the distance between the y-axis and x equals y to the fourth, which is just y to the fourth. Okay. So, let's see here. This is pi times 4 minus 4y squared plus y to the fourth minus pi times y to the eighth. So pi times 4 minus 4y squared plus y to the fourth minus y to the eighth. Okay. And so the volume is going to be the integral of that. Now, what would be the bounds? Well, we're integrating along the y-axis now. So the bounds need to be from the y-coordinate of this point to the y-coordinate of this point. Those would be the locations where these two curves intersect. So we just have to set these two curves equal to each other. So 2 minus y squared equals y to the fourth. This gives us 0 equals y to the fourth plus y squared minus 2. That gives us 0 equals y squared plus 2, y squared minus 1. That gives us 0 equals y squared plus 2, y minus 1, y plus 1. So we get two solutions here, y equals 1 and y equals negative 1. Naturally, y equals negative 1 is here, and y equals 1 is here. So, negative 1 to 1. Okay. So, this is pi times 4y minus 4/3 y cubed plus 1/5 y to the fifth minus 1/9 y to the ninth, evaluated from negative 1 up to 1. And literally, that comes out to be pi times 4 times 1 minus 4/3 1 cubed plus 1/5 of 1 to the fifth minus 1/9 of 1 to the ninth minus pi times 4 times negative 1 minus 4/3 of negative 1 cubed plus 1/5 of negative 1 to the fifth minus 1/9 of negative 1 to the ninth. How you choose to write this is, again, unimportant, but it does come out to be 248 pi divided by 45. Okay. And let's do one more like this. This is the region bounded by y equals x cubed, y equals 0, and x equals 1. Again, revolving around the y-axis. So, as always, we'll draw a diagram. Y equals x cubed looks something like this. Y equals 0 is just the x-axis. And then x equals 1 is this line right here. So, it's this region. We're going to revolve this around the y-axis. All right, well, in that case, we should take a typical slice perpendicular to the axis of rotation, so something like that. You revolve this around the y-axis, what you'll get is a washer, once again. And so once again, we're tasked to find the, our task is to find the inner and outer radii. In order to do that, we should write y equals x cubed as x equals the cube root of y. Because everything is going to have to be in terms of y if we're going to integrate with respect to y. So, this is pi times, let's see, outer radius is going to be x equals 1. Inner radius is going to be cube root of y. And so we're working with something like that. So, this is just pi times 1 minus y to the 2/3. The volume is then going to be the integral of pi times 1 minus y to the 2/3 dy. And we need to think about what the bounds are. Well, the lower bound is just 1, the lower bound is just 0, because it's just the line y equals 0. The upper bound is the y-coordinate where x cubed and x equals 1 cross, which is just where y equals 1. So 0 to 1. You do this antiderivative, we get pi times y minus 3/5 of y to the 5/3, evaluated from 0 to 1. This is pi times 1 minus 3/5 minus pi times 0 minus 3/5 of 0. And again, the way that we write this is not important, but this does come out to be 2 pi over 5. And so that is the volume that we get when we rotate this region around the y-axis. Okay? So that does it for volumes. We'll see if I ever upload a video about volumes by cylindrical shells, because that's a different method for doing the same thing. In any case, homework is up. Get some practice with that.